This problem gives us a sphere of radius r with a charge q spread over its surface and asks us to find the potential V at three different locations. One at twice the sphere's radius, the second on the sphere's radius, and the third at half the sphere's radius. The potential at any distance r from the center of the sphere relative to infinity is the line integral of the electric field over the path. If we take the potential at infinity to be 0 and reverse the order of the limits on the integral, we get this expression, which shows us that we need to know the electric field before we can evaluate the potential. We know from Gauss's law that the electric field outside the sphere is the same as that of a point charge, q over 4 pi epsilon naught r squared in the r hat direction. Also from Gauss's law, we know there is no electric field inside the sphere. So we can use these expressions to evaluate the potentials outside and inside. The potential outside is minus the integral of the electric field outside over the path from infinity to r. When we substitute the expression for the electric field and integrate, we find the potential outside the sphere is the same as that of a point charge, q over 4 pi epsilon naught r. The potential inside the sphere is minus this integral, evaluated from infinity to a point inside the sphere. This electric field changes as we cross the boundary from outside to inside, so we need to break the integral up into two, one having the electric field expression outside, and the other with the electric field expression inside. The second integral we know is 0 because there's no electric field inside. And that shows us that the potential everywhere inside the sphere is equal to the potential on the surface, q over 4 pi epsilon naught capital R, the sphere's radius. Now we can answer parts A, B, and C. We know the sphere's radius is 24 centimeters, and we're asked first to find the potential at twice that distance. So we can write the expression and substitute in the known values, including this for the Coulomb constant. Finding the potential at a distance of 48 centimeters is 65.6 volts. In part B, we're asked to find the potential at the sphere's radius. So we can substitute that value of r into the expression, or realize that because the potential goes as 1 over r at half the radius, the potential is going to be twice its previous value. Either way, we find the potential is 131 volts. In part C, we're asked to find the potential inside the sphere at half the radius. The potential inside the sphere is always constant and equal to the value on the sphere's surface. So that gives us the same value as in part B, 131 volts.